Astronomers have just uncovered what should be impossible: powerful waves of heat radiating from deep inside interstellar object 3I/Atlas. Infrared telescopes across the world confirm the signal, hotspots blazing from its core, far beyond what sunlight or cosmic decay could ever explain. Comets are supposed to be frozen wanderers, yet Atlas, a 44 billion-ton visitor on a one-way flight through our solar system, burns from within. Its energy outshines theory, leaving even the world's top physicists in disbelief. If comets can't generate heat like this, what force is pulsing inside Atlas? And what happens if that force is unleashed? Each detection arrives as a data stream, pixels and spectra, not just images. The James Webb Space Telescope, operating at 3.3 astronomical units from the Sun, captures thermal signatures in the near and mid-infrared. Its NIR spec instrument, tuned to the faintest heat, isolates emission lines from carbon dioxide, water, and carbon monoxide. But the surprise isn't in the molecules, it's in the map of temperatures. JWST's spatial resolution, down to a few hundred kilometers at this distance, reveals clusters of warmth near the nucleus, hotspots that persist even as the comet rotates. ALMA, the Atacama Large Millimeter/Submillimeter Array in Chile, confirms the story from another angle. Its array of dishes, spread across the high desert, tracks the same regions in submillimeter wavelengths. The data show not only a rich spectrum of volatile gases, but also pockets of elevated thermal emission, distinct from the rest of the coma. Ground-based infrared arrays, including VLT and Gemini South, report similar findings. Their adaptive optics and polarimetric imaging cut through the coma's glare, reinforcing the pattern. Heat is emerging from within, not just from sunlit ice at the surface. Cross-checks run through the global observing network. Each facility's raw FITS files are processed independently, calibration stars and background subtraction meticulously logged. Reduction teams comb through the data for instrument artifacts, persistent hot pixels, cosmic ray hits, and background mismatches. The hotspots remain, surviving every challenge. Signal-to-noise ratios reach as high as 90 in key bands. Confidence intervals shrink as more epochs are added. By late August, the evidence is irrefutable. Internal logs from the JWST team describe a mood of collective disbelief. A senior scientist writes, "This kind of heat signature is unprecedented in comet science." At the VLT, junior astronomers flag the anomaly in their Slack channel. Hotspots? Or did someone hack the pipeline? Public figures weigh in. Neil deGrasse Tyson, asked on live television about the possibility of artificial heat, responds with characteristic calm. Nature is not obliged to conform to our expectations, but this is not what we expect. The credibility of the data is no longer in question. The question now is what it means. Physics textbooks describe comets as ancient, frozen leftovers, their interiors colder than liquid nitrogen, and their energy budget dictated by the sun. For 3I/Atlas, the numbers refuse to add up. The nucleus weighs in at an estimated 44 billion tons, yet the heat detected by infrared telescopes suggests an internal energy source far beyond what sunlight alone can provide. Standard models offer little comfort. Radioactive decay, the slow burn of isotopes like uranium and potassium, is the only long-term heat source expected inside a cometary core. But for a body this size, calculations show less than a single watt of decay power remains, barely enough to light a Christmas bulb, let alone drive measurable warmth across kilometers of rock and ice. Other natural processes fall short. The crystallization of amorphous ice, a one-time release of latent heat, would be spent after a few million years adrift between stars. Chemical reactions, oxidation, clathrate breakdown, phase changes, produce short, sporadic bursts, not the sustained, localized hotspots seen in the data. Even the most optimistic models, stacking every possible energy source, can't explain the scale or persistence of the observed heat. The situation leaves veteran physicists shaking their heads. In a televised interview, Michio Kaku puts it bluntly, "If these measurements hold, we're looking at a violation of everything we know about comet interiors. Nature is supposed to be stingy with energy, especially in the cold dark between stars. But here, the math just doesn't close." The disbelief echoes through meeting rooms and online forums. Teams rerun their reductions, hunt for calibration errors, and debate the possibility of unknown supervolatiles or hidden exothermic chemistry. Yet every attempt to balance the books runs into the same deficit. The heat is too strong, too focused, and too steady to fit the playbook. The data demand a new explanation, one that may force scientists to rethink the boundaries of comet physics itself. The question now isn't whether the heat is real, it's what could possibly be generating it, and why the rules seem to be breaking in the presence of 3I/Atlas. SphereX, scanning in the near-infrared, logs a pattern that refuses to flatten out. Instead of a steady warmth, the heat from 3I/Atlas rises and falls in a cadence that repeats every 3 hours and 17 minutes. Each pulse registers as a distinct spike in the thermal light curve, rising sharply, then fading before the cycle repeats. The effect is unmistakable in the phase-folded analysis. Stacking the data by period, the peaks align like clockwork. Cross-checks with optical observatories reveal a matching rhythm. When the heat surges, so does the comet's brightness in visible light. The two signals, thermal and optical, march in lockstep, reinforcing the reality of the phenomenon. It's not a random outburst or a one-off flare. The pulses persist across multiple nights, through different instruments and under varying observing conditions. Instrument teams run through the usual gauntlet of artifact checks. Detector persistence, cosmic rays, background subtraction errors, all ruled out. The signal-to-noise ratio remains high, and the periodicity holds even after aggressive data cleaning. For comets, such regularity is unheard of. Natural jets and outgassing are chaotic, driven by sunlight and surface features, not an internal metronome. Yet here, the evidence points to a hidden process deep inside Atlas, cycling with mechanical precision. The anomaly has shifted, no longer a static mystery, but an active, pulsing engine. The next question is what could be driving such a rhythm beneath the surface? Harvard's Planetary Science Group enters the debate with a different premise. What if the nucleus of 3I/Atlas is not solid through and through, but instead riddled with internal cavities? Their models, published in late August, simulate a shell just a few hundred meters thick, surrounding a porous or even hollow core. In these scenarios, heat from solar-driven outgassing could seep inward, linger, and then vent outward in concentrated bursts. The thermal conduction rates for cometary material, measured in laboratory analogues, are staggeringly low, often less than 1,000th that of solid rock. This means even shallow cavities can act as reservoirs, trapping warmth for hours before sudden release through narrow vents. The Harvard simulations test a range of shell thicknesses. Too thin, and the structure would collapse under its own weight. Too thick, and the observed heat could never escape fast enough to match the infrared maps. Their sweet spot, a shell of 200 to 400 meters with vent channels no wider than a subway tunnel. Gas pressure builds in these pockets until the overlying dust mantle gives way, unleashing a focused plume of heat and gas, potentially explaining the thermal spikes seen by JWST and ALMA. In a press briefing, lead researcher Dr. Lee remarks, "If there's a hollow, it changes everything. The heat isn't just a surface trick. It's stored, then vented, like a geyser beneath the ice." The theory remains speculative, but it offers a mechanism for storing energy deep inside Atlas, challenging the long-held view of comets as inert, frozen relics. For the first time, the possibility of a dynamic, layered interior enters the mainstream conversation. On November 29, 2025, 3I/Atlas reaches the point in its orbit where it crosses the Mars corridor, an invisible boundary that, on paper, separates routine astronomical observation from planetary concern. Inside government offices and agency control rooms, the mood turns watchful. The US National Space Council convenes an emergency session, joined by ESA representatives and Mars mission planners. Declassified memos, later leaked to the press, reveal a flurry of late-night communications, requests for updated ephemerides, rapid response tracking assignments, and contingency plans for satellite maneuvers above Mars. The European Space Agency issues a quiet directive to its Mars Express and ExoMars Trace gas orbiter teams. Review orbital parameters, prepare for possible adjustments, and increase atmospheric monitoring cadence. NASA's Deep Space Network is tasked with round-the-clock telemetry, not for fear of collision, but to capture any hint of erratic motion or unexpected activity as Atlas approaches the zone where Mars and cometary debris have intersected before. Behind closed doors, policy analysts debate the odds of an active interstellar object releasing energy or material near a planet. The question on classified briefings is not just about scientific curiosity, but about risk. Could a self-heating nucleus trigger an outburst as it passes Mars? Would a sudden plume threaten satellites or seed the thin Martian atmosphere with exotic compounds? SpaceX, preparing for a late 2025 launch window, quietly accelerates reviews of shielding protocols for its Starship hardware. The official line remains calm, but the classified record shows a rare convergence of science, engineering, and policy, each forced to reckon with a visitor whose behavior defies easy explanation. Inside the conference rooms at NASA's Jet Propulsion Laboratory, the whiteboards fill with equations and cross-sections. The standard playbook starts with exotic ices: carbon dioxide, carbon monoxide, even the rare carbonyl sulfide, each one more volatile than water, each capable of driving activity far from the sun. Laboratory tests confirm that carbon dioxide can sublimate at temperatures barely above 80 Kelvin, and at 3 astronomical units, sunlight delivers just enough energy to liberate these ices from near-surface layers. The models are clear: shallow pockets of carbon dioxide-rich ice, exposed by fractures or thin dust mantles, should produce steady outgassing and a faint, cold coma. But the numbers from 3I/Atlas refuse to fit. The observed heat output dwarfs what solar-driven sublimation alone can provide, even when the carbon dioxide inventory is pushed to the highest plausible value. When modelers try to match the pulse cadence, 3-hour cycles, sharp thermal spikes, they run into a wall. The recharge time for gas pressure in a porous nucleus at these temperatures is measured in days or weeks, not hours. The predicted temperature curves lag behind the observed peaks, and the amplitude falls short by an order of magnitude. Internal memos circulate as teams tweak every variable: porosity, grain size, dust layer thickness, cavity geometry. Still, the simulations produce only slow, irregular venting, none of the rhythmic focus bursts mapped by the telescopes. A JPL scientist writes in frustration, "We can stretch the chemistry, but not the clock." The consensus: exotic ices explain the coma's richness, but not the interior's heat. The accepted physics is running out of room. Avi Loeb, chair of Harvard's astronomy department, enters the debate with a calculation that refuses to be ignored. If 3I/Atlas truly radiates from within, the power required is staggering, on the order of megawatts, not milliwatts. That's reactor territory. Loeb's memos, circulated among colleagues and later published in preprint, pose a blunt question. What natural process could deliver this much energy on a schedule from a frozen body born between the stars? His analysis draws on the thermal maps from JWST and ALMA. The hotspots are not diffuse. They cluster, pulse, and, most provocatively, sometimes share the same temperature profile as smaller objects moving alongside Atlas. These so-called companions, faint in the optical but bright in the mid-infrared, match the nucleus's heat curve to within a few percent. Loeb points out that, if these are fragments or satellites, their synchronized warmth suggests a common energy source, not just sunlight bouncing off dust. He frames it with a metaphor. If it's periodic, that suggests a clock, and nature rarely builds clocks for fun. The implication is hard to miss. In Loeb's scenario, the interior of Atlas could house a mechanism: an engine, a reactor, something engineered to produce and distribute power. It's a hypothesis that divides the room. For some, it's a leap past the data. For others, it's the only explanation left standing when every natural model fails to close the energy budget. The artificial power source theory, once fringe, is now on the table. 3 interstellar visitors, 3 sets of puzzles. In 2017, Oumuamua entered the solar system as a tumbling, cigar-shaped mystery. Its trajectory shifted in ways gravity alone could not explain. No coma, no jets, just a silent acceleration, sparking debates over outgassing, radiation pressure, and the wild idea of artificial propulsion. 2 years later, Borisov arrived. This time, the behavior matched expectations. A classic comet, rich in volatiles, shedding dust and gas in a familiar arc. Its chemistry and outflow fit the models, offering comfort to those who prefer the cosmos to play by the rules. Then comes Atlas. Larger by orders of magnitude, heavier than either predecessor. Its nucleus, estimated at 44 billion tons, radiates with an energy signature that doesn't fit the pattern. The heat isn't diffuse, but clustered. Hot spots that pulse in rhythm, sometimes echoed by smaller companions tracking alongside. The chemistry is stranger still, a carbon dioxide to water ratio higher than any comet on record, with outgassing that began long before sunlight could have reached the core. 3 objects, each more confounding than the last. Non-gravitational motion, unexpected activity, now a comet that seems to break every rule. The pattern is hard to ignore. With each arrival, the boundary between natural and engineered grows thinner. If Atlas is the next step, the question lingers. Is the solar system a crossroads, or a testing ground for something we have yet to understand? At 3.3 astronomical units from the Sun, infrared telescopes detected persistent heat radiating from the core of 3I/Atlas, an interstellar object weighing roughly 44 billion tons. Multiple observatories, including JWST, ALMA and VLT, confirmed localized hotspots and rhythmic pulses of warmth that standard comet physics cannot explain. Decay and chemical reactions fall short by orders of magnitude, and mainstream models fail to account for the concentrated, engine-like energy patterns deep inside the nucleus. Despite extensive analysis, no natural process has matched the observed cadence or intensity. Harvard simulations suggest hollow cavities, while some experts propose reactor-level power sources. As of September 2025, Atlas is on course to cross Mars's orbital path, prompting international monitoring and risk assessments. The true source of the heat remains undocumented, with key observation files still under review. The evidence stands. 3I/Atlas challenges every expectation of interstellar comets, and its core remains an unsolved scientific mystery.